Hello everyone, I am Shwechran. Today I'm going to talk about bootstrap resampling to quantify uncertainty and aerodynamic drag measurements. This corresponds to the course of probability and statistics. And yeah, coming to the topic itself. Mhm. Introduction to bootstrap resampling in aerodynamics. Bootstrap resampling is a statistical method used to eliminate the uncertainty of measurements by repeatedly sampling from the observed data. In aerodynamic drag testing, it helps in quantify confidence intervals and variability in drag measurements. This technique is especially useful when underlying data distribution is unknown or difficult to model analytically. So, coming in detail, bootstrap resampling is a statistical method used to estimate the uncertainty and measurements by repeatedly sampling the observed data. So, in this bootstrap resampling, we take repeated measurements by using repeated sampling from to the observed data. This bootstrap resampling works statistically uh, to estimate the uncertainty in the measurements. In aerodynamic drag testing, it helps quantify confidence intervals and variability in drag measurements. This corresponds to aerodynamics in the drag testing, like the aerodynamic drag of the flight mechanics. This bootstrap resampling it helps in quantifying confidence intervals and variability in these drag measurements. This technique is especially useful when underlying data distribution is unknown and difficult to model analytically. So this bootstrap recycling is very useful to find the underlying data distribution, how the underlying data is distributed according to uh, for which is unknown or difficult to model the given data distribution analytically. And coming to importance of quantifying data uncertainty in drag measurements. Accurate drag measurements are essential for optimizing aerodynamic performance and fuel efficiency. Uncertainty quantification provides insight into reliability and repeatability of experimental results. Understanding measurement variability helps in making informed decisions during design and testing processes. So these drag measurements are accurate. Accurate drag measurements are essential for optimizing aerodynamic performance and fuel efficiency. So this must be essential. They must be accurate and are essential for optimizing aerodynamic performance and fuel efficiency. Uncertainty quantification provides insight into reliability and repeatability of experimental results. Understanding measurement variability helps in making informed decisions during design and testing processes. So this uncertainty in quantification, this provides insight into reliability and repeatability of experimental results. This can be repeatable and are reliable to get the results, experimental results. Understanding measurement variability helps in making informed decisions during design and testing processes. Coming to basic process of concept of bootstrap resampling. The bootstrap involves generating in many new datasets called resamples by randomly sampling the replacement with original data. Each sample has same size as the original dataset but may contain duplicate values. By analyzing these values, we can estimate the variability of measurement statistics such as mean drag coefficient. So this involves generating many datasets which are called resamples by randomly sampling them with replacement from the original data. So all this work is by generating many datasets uh, in which data is randomly generated from the original data, which are sampled into these replacement datasets, which are called resamples. This is how the name it called resampling. Each resample has a size as the original dataset, but may contain duplicate values, multiple values. By analyzing these resamples, we can estimate the variability of measurement statistics, such as the mean drag coefficient. In the aerodynamics, the mean drag coefficient, which can be by many of the examples we got from this bootstrap resampling, we can get the mean drag coefficient. Steps to perform bootstrap resampling. Collect a set of aerodynamic drag measurements from experiments or simulations. Generate a large number of bootstrap samples by randomly selecting data points with replacement. Calculate the statistic of interest, like the average drag coefficient for each bootstrap build uh, to its distribution. At first, we need to collect a set of aerodynamic drag distributions from experiments or simulations. We need to generate a large number of bootstrap samples from those the original data by randomly selecting data points from the replacement. We need to calculate the statistic of interest like the average drag coefficient for each bootstrap sample to build its distribution. So the statistic of interest, like the average in the original data, such as the average drag coefficient, uh, we need that uh, for each bootstrap sample. For every sample, we need that for to build its distribution across the many. Coming to estimating confidence intervals for drag measurements, use the distribution of the bootstrap statistic to determine confidence intervals such as the 95% interval. Common methods include percentile-based bias corrected or accelerated bootstrap intervals. These intervals provide bounds within the true drag measurement likely resides. Coming to advantages of bootstrap resampling in aerodynamics. Bootstrap makes minimum assumptions about the data's underlying distribution. It is flexible and applicable to smaller complex datasets typical in aerodynamic testing. This method provides a straightforward way to assess the uncertainty associated with experimental data. So this makes minimal assumption about data's underlying distribution. This bootstrap the resamples are flexible and applicable to even smaller complex databases typical in aerodynamic testing. Like this can be used in either are small or either in complex at the same time. This method provides straightforward way to assess the uncertainty associated with experimental data. Coming to limitations and considerations, Bootstrap assumes that the sample data are representative of the population, which may not always hold. Results can be sensitive to outliers or non-independent data points. Computational cost increases with number of resamples, but modern computing often mitigates this issue. So Bootstrap assumes that the sample data are representation of the population. Uh, so how this works is by the original data, which are divided into resamples, the resamples, which correlates the sample data. So this bootstrap assumes that the sample data are representative of the population, which may not be the same, which may not be wrong, which may be correct. So these results, the sample can be sensitive to outliers or not independent data points. So the compilation count increases with number of resamples, but modern computing often mitigates issue due to the uh, com- modern computers, they may find the common points and may reduce the computational costs, which may help us better utilize this process. And here is a practical example of drag coefficient measurements. Suppose we have a dataset of 30 drag coefficient measurements from wind channel tests. We generate 10,000 bootstrap samples by resampling with replacement. Calculating the mean for each sample creates a distribution from which confidence intervals are derived. So through this, through the 10,000 bootstrap samples, by creating the mean sample through all these 10,000 various samples, it creates a distribution where confidence intervals are derived. Coming to interpreting bootstrap results, the spread of bootstrap distribution indicates the measurement's variability. Narrow confidence intervals suggest high precision, while wider intervals indicate greater uncertainty. These insights can guide decisions about experimental validation, design or model validation. The spread of bootstrap distribution indicates the measurement's variability. So the spread, like how these bootstrap resamples are distributed, this indicates the measurements variability, how variables they are. Narrow confidence intervals. This against high precision, while wider intervals indicate greater than in the previous example, we talked about it. There are 10,000 bootstrap resamples. For all which there should be a mean variable. So which is the confidence interval. So there is a small narrow difference which will be highly precise because there is a narrow difference. The result may be nearly the same, but if there are varied intervals, there may be a complex issue and there is much more we have to know. We have to account for. We need to do even more complex calculations to get the proper average value. These insights can guide decisions on experimental design and model validation. Yep. Coming to the next, software tools for Bootstrap resampling. Many statistical software packages such as R, Python, and MATLAB include Bootstrap functions. In R, the boot package simplifies resampling and confidence interval calculations. Python's scikit-learn and stats models libraries also support Bootstrap and this for statistical analysis. So there are many software packages for different types of programs such as there is the R, Python, and MATLAB. In R, the boot package simplifies resampling and confidence interval calculations. These two are the main in the Bootstrap resampling processes. In Python, there is scikit-learn and stat model libraries to support Bootstrap methods. We can use these libraries in the program to use the Bootstrap resampling process. And coming to summary and key takeaways, Bootstrap resampling is a powerful non-parametric method for quantifying uncertainty in aerodynamic drag measurements. It provides confidence intervals that help assess the reliability of experimental data. Proper application of Bootstrap techniques enhances the robustness of aerodynamic performance evaluations. So this bootstrap evaluation is a powerful non-parametric method through which we can remove the uncertainty in this aerodynamic drag measurements. We can get a certain uh, the proper amount, the proper mean value we need to get from the various B samples we get to this process, which may be highly accurate due to its very complex calculation. This provides confidence intervals that help assess reliability of experimental data. Without the use of practical models, through this experimental data, through this experimental resampling, we can get confidence intervals. If they are narrow, it means the confidence intervals are narrow. It means the data is reliable. If they have a wide gap, these may not be reliable. Proper application of bootstrap techniques enhances the robustness of aerodynamic performance evaluation. So the proper execution enhances the robustness and gives us the proper clear-cut conclusion which we need. Coming to the conclusion, incorporating bootstrap resampling into aerodynamic testing improves measurement confidence and decision making. Future research may focus on adapting bootstrap methods to complex turbulence methods and unsteady flows. Continued advancements in computational power will facilitate more extensive and accurate uncertainty analysis in aerodynamics. Well, incorporating bootstrap resampling into aerodynamic testing, like incorporate this particular resampling method into aerodynamics, this improves the measurement confidence and is also improves the decision making, uh, which are used in getting the resamples. Future research may focus on adapting these bootstrap techniques to complex turbulence models and unsteady flows. To do more simulations and to get the proper accurate data. Continued advancements in computational power will facilitate more extensive and accurate uncertainty analysis in aerodynamics. And yeah, this is my presentation. Thank you. Thank you for listening to the presentation.